Okay, so let's start with the second talk of the morning session. And I'm grateful to have Dr. Noshita from the University of Tokyo, now moving to Peking University. And he's going to talk to us about gauge origami and BPS QQ characters, Donaldson Thomas and PTQQ characters. Please go ahead.
Thanks for the introduction. I'd like to thank the organizers for giving me the opportunity to talk here today. It's my first time being in Korea. So far, everything nice. And today I will be talking about Donaldson Thomas and Conde Thomas QQ characters based on recent works with Taro. So let me give a brief introduction. So as we all know, supersymmetric gauge series in the omega background have revealed a remarkable interplay between geometry, physics, and representation theory. And in particular, the Nekrasov partition functions admits an infinite set of non-perturbative Dyson-Schwinger equations. And they are related to the symmetries of adding and removing instantons, which lead to the concepts of like BPS algebras. And what I'm going to talk today is the QQ characters. And QQ characters are some physical observables characterizing them. And they have various characteristics. An example is like they are quantum analog of the cybercritian curve. They also have applications to BPS safety correspondence or AGT correspondence. Or from the quantum algebraic perspective, they are understood as generators of deformed diagonal algebras. And they also have relation with quantum toroidal algebras. And as an example of applications of them, we have applications to integrable systems like TQ relations, transform matrices, intertwiners, and also R matrix. And my recent interest is to generalize the concept of QQ characters as much as possible. And what recently I'm doing is to generalize the QQ characters to physical systems related with toric Calabi-Yau fourfolds. And basically, what I'm currently doing is two directions. One is the what we call toric BPS square QQ characters, and given square diagram and the associated supersymmetric quantum mechanics, we can construct a large class of QQ characters. And brain tilings, brain brick models, everything are the basic ingredients to lead this type of QQ characters. And the other direction I'm currently doing is the concept of webs of BPSQQ characters. And giving some kind of brain web, we can associate QQ characters onto the vertices of it and introduce some type of gluing. But for the moment, both of them are still, we're still doing it. It's still in progress. But in this talk, I would like to talk about this part. And since it's still not complete, I will be focusing on how to introduce QQ characters associated with the vertex. So they are the DT and PT QQ characters. So all of the stories of QQ characters start from this gauge origami. So let me briefly introduce it. So Nekrasov introduced a concept of generalized gauge theory, where the gauge theory is the space-time of it contains like several intersecting components. So for each component, you'll have a gauge group, and also in the intersection, you'll have some kind of matter fields. And in this sense, you can understand it as a generalized quiver gauge theory. And one example of it is the gauge origami. And the gauge origami system is a theory arising from the lower energy limit of multiple intersecting D branes. So for example, if you consider like a type 2 string theory on Z times R2, where Z is C4, you can think of multiple types of subspaces in the C4, like you have C, C2, C3, and C4. And it can be described in this tetrahedron here. The vertex are given the C, and the edges are given the C2, and the faces will be C3, and the total tetrahedron will be the C4. And you can wrap D branes on each of those subspaces. So for example, we have 6 types of D5 branes depending on which C2 we wrap. And we can choose D1 branes wrapping the remaining two-dimensional space. So this is an example of the brane. But general D branes construction will not preserve enough supersymmetry, but under suitable B field, you can the system will preserve 2 supersymmetries. And if you focus on the D1 brane probing this C4, it will be a 2D n equals 0, 2 quiver gauge theory. So let me briefly review the ingredients of this 0,2 quiver gauge theory. So we have three fundamental superfields, vector, chiral, and Fermi. And additionally, we have the information of the E term and J term. And depending on what kind of geometry you're thinking, you have extra flavor symmetries. And you can also generalize the story to quiver gauge theories. And I'll write the nodes as this and the edges like this. And for each node, you'll have a gauge group. And for a black oriented edge, you can associate the chiral superfield. And colored oriented edge, you can associate the Fermi superfield. And given this low energy system, you can think of the width index, which gives, at the end, becomes the instant partition function of this theory. So we take triviality along the 2D space and think of type 2A string theory. Then the D0 branes will be probing D4, D6, and D8. And this will be a one-dimensional n equal to supersymmetric quantum mechanics now. For the gauge origami system, we have U1 3 flavor symmetries, which I will write Q1, Q2, Q3, Q4, and equals 1. We have three independent parameters. And at the end, they will be related with the parameters, the Q deformation parameters of the algebra. And we can think of the partition function by studying the width index of this quantum mechanics. So let me introduce basic partition functions of this C4. So if you focus on C4, we have three setups: spike instanton, tetrahedron instanton, and also the magnificent 4. So for the spike instanton, we can place 6 types of D4 branes along the C2 and probe it with these branes. For the tetrahedron instanton, you can wrap 4 types of D6 branes for the C3 subspace. And for the largest one, you have the magnificent 4, where we are wrapping the D8 brane over the whole C4 with D0 branes probing. And the quiver diagram will look like this. And we can also think of the J terms and E terms. For example, the magnificent 4 J terms and E terms will look like this. And using these J terms and E terms, you can also determine the flavor symmetry of the quantum mechanics. And I will associate the flavor charges to the quiver diagrams in this way. And later, when we derive the algebras from the quiver diagram, all these parameters will be important. Then you can compute the partition function using the JQ residue formalism. And generally, all the system will look like in this form. So once, for example, if you think of a spike instanton, the counter integral will factorize into the D0, D0 contributions and also the D0, D4 contributions. So for example, this one is the D0, D4 setup. So this one is the D0, D0 contributions, and this one is the D0, D4. And you can read from, so given the flavor charges, you can write down the with the index and compute the counter integral. And as is well known, if you evaluate the poles from this counter integral, it will be expanded in Young diagrams. But since you have like 6 types of different D4 branes, the Young diagrams will be spanned by 6 types of Young diagrams. And the parameters spanning the Young diagrams will be depends on what type of D4 brane you're thinking. So if you are spanning a D4 brane on C2 with extending in the first and second direction, then the parameters will be like Q1 and Q2. And if you move on to the tetrahedron case, you will have 3 parameters, Q1, Q2, Q3. And if you if you study the JQ residue, they'll be expanded in plane partitions, which I denote here like pi. And the most interesting setup is the magnificent 4. And in this case, the poles will be classified by 4-dimensional versions of the Young diagrams and also plane partitions, which I'm illustrating like this. So a sequence of plane partitions extend in the 4th direction. And yeah, so this is called the solid partitions. And the partition functions will look like in this way. So the concept of deriving QQ characters is to find a nice free field realization of these partition functions so that you can establish the BPS CFT correspondence. So given this, I didn't write the formulas here, but given this counter integrals and also the expansion of the partition functions, you'd like to construct a nice operator version of it. And it's interestingly, this free field realization, the counter integrals and also the partition functions appearing in all the systems have a nice free field realizations. So let me give a general construction how to derive all the vertex operators that appear in the theory given a 2 SUSY quiver. So let Q bar to be a 2 SUSY quiver, and you have J terms and E terms, and assume that you can determine all of the flavor charges given these J terms and E terms. And for the moment, I will be only focusing on the quantum mechanics where the gauge groups are all unitary type. And given these flavor charges, you can write down what we call positive half cubiform quiver Cartan matrix. So given a quiver diagram, you add some diagonal term, and for each edges associated to the chiral fields, you take the difference of the associated flavor charges, and you take the summation of the Fermi flavor charges. Then you define total quiver Cartan matrix by taking the Hermite conjugate of it. So this one means the conjugate of it. So flipping all the signs to the inverse and define this quiver Cartan matrix. Then after you do this, you define a nice vertex operator obeying this free boson relations in this way. And for example, the vertex operators will be decomposed into two parts, like non-zero modes and also non-zero modes and zero modes. And the zero modes will be determined by this Heisenberg algebra. And this one here means replacing all the parameters to the power of n. Then generally, if you consider like unitary groups, the width index have a free field realization in this way. And the integral will be taking over flavor fugacity of the gauge nodes. But for flavor nodes, we don't need to take the integral. And the operator product here will be at the end for the flavor nodes that you don't take the integral will be understood in this way. Then after you expand all of the, so each of the vertex operators here will have non-trivial contraction with each other. So after you compute it, it will reproduce this free field realization will be composed into two parts. One will be the rational functions written in Shinch functions, and the other one will be an operator part. So in this way, you can get an operator lift up of the width index of the partition functions. And actually, this procedure will give what I will call the QQ characters. And this procedure is actually a generalization of the original work by Kimura-Peston, where they introduced the concept of quiver Cartan matrix. And in their theory, the quiver structure appearing was 8 SUSY quiver, but what I'm doing now will be 4 SUSY and 2 SUSY quivers. So it's a large generalization of their work. So this is the general construction of like one-dimensional 2 SUSY gauge theories, and you can apply it for the gauge origami system of C4. So and for each, since the flavor nodes of the associated gauge origami system is classified into three types, like D4, D6, and D8. For each flavor nodes, you can introduce a new type of vertex operators, which we call D4, D6, and D8 vertex operators. And for the contribution coming from the D0 brane, you can also associate a vertex operator, which I call the D0 brane operator. Then analogously, you can introduce a different D2 brane operator, but the physical implication of this D2 brane operator is still not known. But anyway, you can introduce this type of vertex operators, and if you combine them, at the end, they will give the operator lift-ups of the width index. And the explicit form will be like this, but as I said a while ago, all the vertex operators are decomposed into zero modes and non-zero modes, and written, and for each of them you can compute you can use the definition and determine the commutation relations between these three modes. So it's quite complicated just writing here. So let me discuss a very simple system, the D0 D6 system. So the quantum mechanics in two-SUSY notation is written like this. So this corresponds to the D6 brane wrapping the C3, and this one here corresponds to the D0 branes. And if you study the low energy theory of the D0 branes, it's just a dimensional reduction of the n equal 4 super mules. So you'll have four n equal 2 chiral superfields and 3 Fermi superfields. And using the J terms and E terms, you can determine the charge as this. And using the general description I mentioned, you can define a positive Weaver-Cartan matrix in this way. So the D0, D0 part, you have a diagonal term 1, and you have the other chiral superlead fields with Q1, Q2, Q3, Q4, and with the summation of these Fermi superfields. And you can also study the contraction between this D0 and D6. So you have one chiral superfield with 1 and one Fermi superfield with Q4. So you define it in this way. But if you take the conjugate of it, and the opposite will be defined in this way. And you can also do the D0, and the D0, D0 will be a summation of this and the dual of it. So after you compute the expansion, you get this form. And also the D0, D6, you get this form. So roughly summarizing, the D0 brane vertex operators have this type of commutation relations, and the D6 brane operators will have this type of commutation relations. And if you use this vertex operators at the end, all of the counter integrals of the gauge origami partition functions can be decomposed in this way. So the A inverse has a physical meaning of the D0 brane operators, and the other remaining operators will have physical meanings of the framing nodes of the associated quiver quantum mechanics. And this setup is quite general. So if you know like the concept of brane tiles and brane brick models, you can also have already large class of n equals 0, 2 quiver gauge series and one dimension n equal 2 supersymmetric quantum mechanics, and you can study free field realizations of it. And this is in a sense one phenomenon of the BPS CFT corresponds. So given a partition function, you have a nice operator lift ups, and if you study the vacuum expectation value of it, you reproduce the partition function. So what I'm explaining here is how to extract the information of all of these operators given a nice partition function and also associated quiver. So I'll just stop for here. Are there any questions up to here before I move to the concept of QQ characters? Okay, so then let me move on to the concept of QQ characters. So as I said, all of the width index here have nice free field realizations, and generally they have the counter integral, the partition function is expanded in this, is written in this form. So what this means is that you have some kind of operator valued infinite sequence, and this is called the QQ character of this theory. And you can also understand it as a deformed double algebra. So for example, for a very simple example is the Q Virasoro. And given the Q Virasoro, but so given this this operators, you like to ask how to think of the operators. Yes.
Oh, can you remind me where was the information of the orientations of the debriefs in the vertex operations?
So the orientations means like here. So how you define the framing nodes, and also it's encoded in so the orientation of where the d-branes wrap is encoded in the framing nodes, and the framing nodes correspond to the this one here.
So V will be different from V.
Yes, yes. So for each d-branes, you can associate a different type of V.
In those in the GK residue there, I mean, is it picked by you?
Yes, so later that will be important, but usually in this context, the reference vector will be picked 1, 1, 1, 1. So the standard one.
You have work the same if you change that or?
Yes, so that will be related to the later talk. For the moment, we don't know all of the swallow crossing effect from this quantum algebra perspective. But so in this talk later, I will discuss two types of eta vector. One is the 1, 1, 1, and the other is -1, -1, -1, -1. And just to answer your question quickly, one will be the dt side and the other will be pt side. So depending on which eta vector you choose, you get two types of QQ characters. And also associated to that, later you'll see that you need to define a different type of screening charge here.
So just a question of terminology. K is the rank of the
K is the number of the instantons. So K is the instanton number. It's not related with the rank of the double algebra. The rank of double algebra is yeah, it's not related to the rank of double algebra.
where is it with that?
K.
No, the uniform project.
So when you say rank, you mean like AA2 quiver or AN quiver, like QVers or QWN?
Yeah.
And that one is reflected in the Cartan matrix. So the definitions of the operators already includes the information of the rank of the different algebra, which also contains the information of the geometry. Okay. So recalling the Sorrow. So given a QVR Sorrow, you'd like to understand the algebraic properties of it. One is the relation with the screening charge, and the other one is the OPE relations of this QVR Sorrow, so which is called the quadratic relations. And to do that, for a general system in the gauge origami, you first need to define screening charges. And for this case, everything is written in the D2 brane vertex operators in this way. So if you're familiar with all this deformed algebra context, this is, I think you're familiar with all of this. But if you generalize it to like Torre-Calvé fourfolds, this part is non-trivial, and how to define it will be a topic that you need to understand. But I won't talk about that. Then, as what you do in the QVR Sorrow, you impose the commutativity with this screening charge and try to determine what kind of algebra you get. And actually, if you think of D4 and D6, if you introduce a nice highest weight of it and study the commutativity, you can automatically determine all of the terms here. So, for example, the D4, if you choose the highest weight associated to the D4, you'll get this type of QQ character, which is known to be the affine quiver double algebra. Or if you choose a different type of highest weight, you'll get an expansion of the deformed double algebra, which takes values in plane partitions. And actually, this matches with the previous definition of the operator lift up of the width index. And
the commutativity of the screening charge, to define the QQ character from the previous definition, then
yes,
it's a statement, right? So it's not like you can fine tune the.
So the problem is that the non-zero modes you can determine uniquely from the quiver diagram, but the zero modes part is a part for the moment you need to fix by hand.
I see. Sorry, but I thought that you even for the zero mode part, you already have the definition and there was no ambiguity.
No. So usually it depends on what kind of quiver you think. Usually the type of quivers we're thinking is like affine quiver types. So if you naively take the Q parameters like 1, everything becomes 0. So you don't have like an inverse of that matrix. So you cannot really define. But in the C4 case, if you impose some conditions, you can write down an explicit form. But that's not unique.
Oh, I see, I see. So in some cases, you already know the canonical thing, so it's just a matter of checking it.
Yes,
In the other cases, you have to kind of get it.
Yes.
Oh, I
So usually you first define some type of screen chart and then impose that it should commute, and then you determine.
I see. So some of the screen, especially the screening charges, you are certainly already certain. You might imagine that you might have to modify that as well.
Yes.
That's not necessary.
Yes.
I see.
And so given this definition of the commutative, the definition of the QQ characters from the viewpoint of the screening charts, you'd like to also study the commutation relation of all of these QQ characters. And our theorem is that you can associate it to each vertex, edges, or faces as a type of QQ characters. And if they are transverse with each other, everything commutes. So, and this is this is one type of the non-perturbative Schwinger-Dyson equations. So usually when you say non-perturbative Schwinger-Dyson equations, when you say it in the quantum algebra, it means you need to commute. But for the D8 case, unfortunately, we don't know the screening chart. So for the moment, the algebraic definition is not so clear. But we can use it. We can stack lower dimensional QQ characters to obtain higher dimensional QQ characters. So for example, if you have a solid partition, you can decompose into slices of plain partitions, and you can associate the D6 QQ character with it and then fuse everything and get the answer. And interestingly, that such kind of derivation also gives the correct magnificent 4 partition function, including the sign rules. So in this way, if for the QQ character, you can start from lower dimensional case. Then since for this case, you don't have the screening charge, but you still like to understand the algebraic properties of it. But so you can also study the quadratic relations of all of these D6 and D8 QQ characters. And an interesting property is that everything commutes also in this case. So first, the most generic D8 QQ character will commute with each other. And if you specialize a special parameter, then it reduces to D6 QQ characters, and which means that at the end, all of these D6 and D8 QQ characters commute to each other. And this is also a new type of non-perturbative Schwinger-Dyson equations. And let me just give a physical, not really physical, but one reason why all of this should commute is because generally if you fuse this operator, these QQ characters, it will be decomposed into 2 parts. So one loop part and also higher rank version of it in this way, and also a vertex operator part. This part increases the rank of the theory, so the the number of the D branes. And assume like this quadratic relations on the right-hand side doesn't commute, then that means that you'll get some delta functions and all those extra operators arising in the right-hand side. Then you take the web of each side, which means if you take the web of these 2 operators, this will give the partition functions of these higher rank versions of the magnificent 4 or tetrahedron instanton. But a well-known phenomenon is that such kind of partition function doesn't depend on the spectral parameters or Coulomb-Branch parameters, and you have a nice PE formula, which means that the partition functions shouldn't have any singularities, which means the QQ character should commute. But unfortunately, this is not true for lower dimensional case. So this is a new phenomenon for D6 and D8 QQ characters. Okay, up to here, are there any questions?
This is also some generalization of the Q-Virasol sense.
Yes.
Which is probably complicated, but in the Q-Virasol, of course, it reduces the Virasol.
Yes.
What happens to this type of algebras? Like
No, this
so equal to 1 and you get something more.
No, we don't know. So for even for the most simple D4 case, the affine fiber W algebra, we don't have all those the undeformed version of it. So we only know the operator formulas, but we don't know what the corresponding CFT is.
I see. But to some extent, you have the algebra, right? So then it should be a vertex algebra.
Yes, so I think so for the D4 case, so that's also a part that people in this field doesn't know. So if you have some kind of affine type, a QQ character associated with affine type, you'll have an infinite sequence of operators, but you don't know how to study the quadratic relations, and you cannot write down in the sense of QV so. But only for this D6 case, so this is one reason I studied it. So if you think of the D6 and D8 case, somehow everything commutes, so you have a nice close relations. So probably starting from this, you can write down the CFT limit, but as you can see, it commutes, so it means it's almost a trivial algebra in the CFT limit. So I think you won't get anything new from this.
Do you know whether there are images of some they talked about like quantum algebra?
So yes, I'm expecting that to be contained some larger algebra with more parameters, but for the moment we don't know. So like for the QV it's a subalgebra of the quantum toroidal algebra, but for the affine fiber algebra, we don't know what kind of subalgebra it is. So it's still an unsolved question, I guess. But just looking at this, it means that already the algebra commutes, so nothing looks interesting from this one. And okay, so I don't have time. Let me move on to the next generalization, which is the Thomas QQ characters. So from now, I'll be focusing only on the Calabi-Yau case because we have a nice algebraic understanding. And a while ago, I said that D6 QQ character has nice plane partitions appearing in the monomial terms, so which means you'd like to change the boundary conditions of these QQ characters. And that is known to be, that is what we call the Donaldson-Thomas QQ characters, or the vertex terms. And to derive the QQ characters, starting point will be the supersymmetric quantum mechanics. And the way to derive the associated supersymmetric quantum mechanics is to start from this minimal plane partition with non-trivial legs and study the 2D lattice projection of it. And you can determine the data of this minimal plane partition by the following sets of vertices. So you have a concave corner, half convex corner, and also full convex corners written in this way. And given these ingredients, you can write down the supersymmetric quantum mechanics and also the Witten index in this. So I won't explain it, but given the elements of this concave corner, the concave corner corresponds to the boxes you can add to this plane partition, and you can associate chiral, a fundamental chiral superfield, or SUSY fundamental chiral superfield in this. And for the other sets of vertices, you can associate the anti-fundamental chiral superfields on this. And then if you study the flavor charges and everything, you can write down the counter integral or the DTG partition function or the K-theoretic equivalent DTG vertex in this way. And the information of the boundary conditions will be contained in this framing node part, and the other part won't depend. And when specifying the counter integral of the JQRST, you need to choose the eta vector to be 1, 1, 1, 1, as this way. And after you do this, you can get the expansion of this will be expansions of all possible plane partitions with boundary conditions. And then you can also study, as what I said, the operator relief up of it. So you have a nice free field realizations where the framing node is encoded in this. And this gives the QQ character of this DT3 vertex. And so the DT3 QQ character will take the form as this. And if you also study the relation with the screening charge, at the end it commutes. And you can also do it in the opposite way. So imposing the commutativity with the screening charge, you can determine the full QQ character uniquely. So basically, the story of this Donaldson-Thomas theory and the associated QQ character is almost straightforward once you determine the nice framing node. But the new perspective will be what will happen if you think of the PT QQ characters. So I think this will be the main part, so I'll focus on this. So as what we know in topological vertex and everything, we have a different vertex known to be the PT vertex or the generalization of the topological vertex. And also this PT counting admits nice box counting expressions. So you start from a minimal plane partitions in this one here. You extend it in both directions and distinguish the intersection into two colors like blue boxes and red boxes. So the blue boxes will be the intersection of only two legs, and the red one will be the intersection of the three legs. And now the box counting rule will be placing boxes inside this hollow structure, and the gravity will pointing a different 1, 1, 1 direction. But additionally, you have complicated rules living in this intersection part here, which I won't review. And an observation is that actually this PT3 partition function can be derived from the same counter-integral formula, but the reference vector will be the opposite, -1, -1, -1. So you have the same counter-integrand here, but everything is, the way you specify the counter-integral will be different. And another interesting property of this is that when at least one of the three legs is trivial, during all of this J-K procedure, only single order poles appear. But when all of the three legs are non-trivial, you'll get higher order poles. And this is also a phenomenon which is not really much discussed in the context of the quantum algebra. So in this way, you can compute the PT partition function. So the question is, do you have an operator lift up of it? And indeed, you have. But before that, let me explain a very simple example, which is the example you have one box for each leg. And for example, in the J-K formalism, if you study the integrand, you get this integrand here. And if you choose the traditional eta vector 1, 1, 1, then you're going to pick this poles here, which is the poles corresponding to the audible poles of the minimal plane partition. But if you take the other eta vector, you get this second order pole. And then you can compute the rest of it, which gives the one instant level of this PT partition function. But a new property of it is that if you study the unrefined limit of it, it becomes 2, which is little different from the usual case. The usual case will become only 1, which corresponds to the usual counting rule of how you add boxes. So this means that at level 1, when you add one box here, it looks like you only have one possibility, but you need to, you have two possibility actually. But everything can be understood from this JK RSD formalism. And actually this corresponds to the type 3 freely labeled box in the original paper, and also a new recent paper discussing a pair of heavy and light boxes in Gaido-Rabchak's paper. But I think I don't have time to discuss this. So, and you can also further do it for level 2. And the JK picks these types of poles. And if you study this specific pole, usually in the context of box counting, you cannot place boxes on the same positions. But for PT counting, you can place because you have a higher order poles. So this is also a different phenomenon from the usual case of the quantum mechanics and also the combinatorial expressions. Then you can also study the operator lift up of it. At the end, since the integrand is the same, you have a similar operator relation, a similar operator lift ups, but the way you specify this integrand will be different. And the counter-integral formula looks like this. And so at the end, to derive the QQ characters, you need to compute this integral. But as I said, if you think of a three legs, so when at least one of the three legs is trivial, since all of the poles are just single order, once you expand the partition, once you expand this this counter-integral expression of the QQ character, the poles will enter here, and you just get a similar expression. But if you think of when all of the three legs are non-trivial, you get second order poles here, which means that the second order poles will also act on these operators. So the QQ characters will be very complicated, and actually you get some derivative terms like this. So this is a new phenomenon also of the QQ characters, which we usually don't think. So we usually don't think of higher order poles, but for this case, you need to think and you need to get all of these extra operators. And the question is, do you have a nice algebraic properties of it? And since the counter integral is all the same, which means the highest weight is also the same. So the question is what kind of screening charge you need. And so you need a new screening charge, otherwise you cannot reproduce the correct QQ character. And the answer is this expression. So usually here you take S4 with power here, but you take a different power here. And then you get the nice PT QQ characters expression. And somehow this should be related to the choice of how you evaluate the counter integral and also the choice of the eta vector. But the general expression for a given eta vector and the corresponding screening charge is not known, but at least for 111 and minus 111, you can get this expression like this. And you can also study the commutativity. When one of the tree legs is trivial, everything commutes. But when all of the tree legs are non-trivial, it's difficult to study commutativity directly. But there is a way to derive all of this Q character, and everything is consistent. Okay, so up to here, I basically introduced new aspects of the QQ characters, of the PDQ characters. And are there any questions up to here?
The two-leg PT character, the screen charge. The last, could you explain the last one?
This one here?
Yes.
Yes. Okay. So so for height, similar to D8 case, you don't have a nice commutation relation with this screen charge. So you need to fuse it. So you start from a PD with two legs only, and then you fuse with a different one-dimensional sequence of screening charge. And if you fuse everything and take a nice limit, you can get it. So, or you can understand. So this one has the highest weight with two legs, corresponding to minimal plane partition with only two non-trivial legs. And you're going to add a different leg in the direction. So you have like this minimal partition here, but to get the general one, you need to add here. So the position of for each position of this one-dimensional rod, you add a screening charge, and you fuse it with this PDQ here.
Okay, I see. That might get, but I suddenly wanted to get the screening charge. The screening charge still the Q4 tilde works, so.
And so this one over here is my no. So this one we don't know how to directly study with the commutativity with this.
But why? Okay, but if you have a complete expression, so you can just.
It doesn't commute. So you have derivative terms, and we don't know how to organize all of these derivative terms. So we don't have a nice expression. We don't know how to.
Yes, let's say again. But how did you solve the problem? That's what I'm trying to yes.
So usually when we don't know how to solve it, we just take all the parameters differently, and automatically this commutes and also this commutes. So we understand it that since all of them commute, they should commute.
Oh, I see. Is it similar as same as the resolving the second order pole?
Yes. But even in that case,
Yes.
if you study the commutativity without resolving, you cannot see the commutativity. Yes. So you need to resolve first. And what I'm saying here is that the resolution is like this.
Oh, okay. I see. But I thought I see. So I thought you wanted to get a screening charge without resolving it. But I see. For that you don't.
For that one, we don't know. And okay, so let me briefly introduce the relation to all of these quantum toroidal algebras. So when we say we want to understand the relations with quantum toroidal algebras, we are focusing on the character aspects of the QQ characters. So for example, in the D6 QQ characters, you'll have terms in monomial terms in plane partitions. So you'd expect the plane partitions since the plane partitions comes from the some representation of the quantum toroidal, the character is related to the character of the quantum toroidal algebra. So let me briefly explain this. So you start from a quantum toroidal algebra, and we have a nice magma homomodule here, and the charge function takes in the form like this. But I'm being loose. So here is actually shifted quantum toroidal, but it doesn't really matter. So the expansion in modes will differ, but at the end it's just the same. And the character of this algebra is just the magma home function in this way. And you can also introduce a generalization of the character, which is the Q character. So you take the trace over the Cartan part and also this degree counting operator, which gives this kind of form. And both of these characters can be derived from the QQ character. So for example, if you take the vacuum expectation value of the D6 QQ character and take the undefined limit, you get the McMahon function. And if you study the contraction with the screening current and take the undefined limit, you get the Q character. So in this sense, the usual D6 QQ character is a generalization of the characters of all of these algebras. Then you can also next consider the DT module, the Johnson-Thomas module. And in this case, everything is similar. So the different parts, how you determine the vacuum, the charge function, and everything is similar. So if you take the undefined limit of the DT QQ character, you get the character of this DT module. And if you study the correlation with the screening charge and take it, you get the Q character of this DT module. But so the question is how you understand the algebraic perspective of this PT module. And actually, it was recently constructed by Gayoto Rapchak in the Mira paper. And the way you construct this PT module is starting from the vacuum charge function of the DT case, you take the inverse of this in this way. And then you also flip the currents of E and F, the roles of the currents of E and F. So usually the currents E will play the roles of creation operators and F will play the roles of annihilation operators. But now you need to flip it. And then if you study it, you start from this charge function, vacuum charge function, and bootstrap all of the algebra. Indeed, you get, for when one of the three legs is trivial, you'll get the usual, the PT counting rules directly from the algebra. But the question is what will happen for the three-leg case? And for this case, again, you have to deal with higher order poles. So it's quite complicated. And I don't think I have time to explain all of this, but the way I'll just give a brief review on how they derived it. So basically, they put ansatz on assuming that the PT counting rules should be satisfied, and try to bootstrap the algebraic relations of it. But since now you have higher order poles coming from the charge functions, you need to introduce a new type of delta functions, which is a derivative of it. Or in the Affine-Yangian literature, it's like you have usually like z minus something, but now you have a double poles in the algebra. But if you do that and try to bootstrap the relation, somehow the action of the Cartan operators won't be any more diagonal, but it will be a non-diagonal. So only a part of the quantum toroidal algebra is reserved for this case. But even so, you can construct all of this PT module. So I will skip this. But then given such kind of module, you can study also the character of it. And it indeed reproduces the undefined topological vertex rate. So that was originally how they introduced this PT module. So the question is how the QQ characters are related to this PT module. And besides the character, you would like to also define the Q character of it. And the Q character will take in this way. So a phenomenon here is that in the first level, you have extra 2 here, which corresponds to the weight, the multiplicity of the level 1. But you also have extra Cartan eigenvalues like this. And then if you study the undefined limit with of the QQ characters, at the end you'll get everything. So the claim is that starting from the QQ character, you can derive all of the character and also the Q characters of the PT module of the quantum toroidal GL1. So also this PT QQ character is some generalization of the characters of the quantum toroidal GL1. So that's one claim. Okay, so up to here, sorry, I think I don't have much time, but up to here, are there any questions? Okay. Okay, so then let me briefly do some higher rank generalizations of it. So it's in like usual gauge theory, you like to increase the number of D branes and what you like to ask what happens. And for rank n DTPT, what you need to do is introduce n types of different D6 branes with boundary conditions as this way. And for the PT and for the DT counting, you just choose the JK raised to in this direction. And for the PT counting, you just take the eta vector in this way. And you can also think of higher ranks like tetrahedron instantons. In this case, you add different orientations of these D6 branes and do the same stuff. And a different generalization is to add also anti-fundamentals to the theory. So in a sense, you have like some supergroup like generalizations. And the way to define it is like you introduce a different framing node contribution by flipping all the equivalent parameters and also changing the fundamental to anti-fundamentals in this way. And what you'll get is that you get a PT counting with the coordinates flipped with the traditional eta vector. And if you use if you flip the sign of the eta vector, you get, on the other hand, the DT counting. So what this means is that you can introduce the concept of DT/PT counting in this way. So on one hand side, you'll have the usual DT counting, and you can also introduce a different. So for example, if you choose the counter integral in this way, if you choose the traditional eta vector, the traditional eta vector will pick here the DT counting in positive coordinates, but picks here PT counting in the coordinates flip by this sign. But if you flip the eta vector to the opposite direction, in this case you get here the PT counting in the usual orientations, and you get here DT counting in the negative directions. So you'll have a higher rank generalizations of all of this DT PT counting. And also you have a tetrahedron supergroup generalization. And you can study everything similar and introduce higher rank QQ characters, and everything is consistent. And just to comment on intrinsic properties, that even for this case, the DT-PT correspondence is hold, for at least for low levels in a physicist level. So not mathematical proof, but you can check it by computer program, and it seems everything works. And also, you like to ask what will happen for Calabi-Yau case, DT4 and PT4 counting. And for the special, the new part of all this DT4 and PT4 is that you have two types of boundary conditions. So one will be boundary, in the usual threefold case, you have Young diagrams in the legs. But for this case, you'll have plane partitions in the four legs. But you also can insert surfaces, Young diagrams into the sixth surface of this fourfold case. And the counting, the JK residue formalism will be similar. You can write everything. You can write down the integrand. You can study, and you can choose the counter integral properly so that you can reproduce both the DT4 and PT4. And a phenomenon different from the threefold case is that, so yeah, for example, if you focus on PT4 with four legs, when you have three non-trivial legs, second order poles will appear. But if you study four non-trivial legs, third order poles will appear. So if you study the operator lift up of the QQ characters and do everything, you get second, when you evaluate the residues, you get second order derivatives. So it's quite very complicated, but you can do it. And also for the surface counting case, for some cases the PT QQ character will only terminate in finite number of terms. But basically, you can do everything in a similar way. But unfortunately, for this case, we don't have any algebraic relations, but at least we can derive everything. Okay, so let me move on. So up to here, any questions? Okay, then I'll just summarize. So this talk, I start from a C4 gauge origami case and choose new types of QQ characters, and they exhibit interesting algebraic properties, and actually they have many generalizations to Calabi-Yau. And from one perspective, I introduced the DTPT QQ characters, and much is still yet to be done. For example, how to understand the DTPT correspondence in terms of the QQ characters. So the usual DTPT correspondence is the correspondence of partition functions, and taking limits of it, you can understand it as correspondence of characters. So a natural question is what will happen for all of these QQ characters, but for the moment we don't know. And another question is how to glue all of them so that you can construct a class of QQ characters associated to some specific brain web. And yes, so that's also a question to ask. And also applications of all of these QQ characters are yet to be studied. So somehow in the literature, all of these infinite sequence type of QQ characters have not much. So for the usual affine quiver double algebra case, there are, and also some orbifold case, there are. But for like those QQ characters associated to the brain tilings or brain models are not known, and also this web, the gluings, the webs of this QQ character are also not yet known. So all of these have to be studied, and I hope someone does this. Okay, thanks for this.
Thank you for the very interesting talk. Any questions?
You mentioned the D6 brain realizing that module for algebra.
Yes.
What does D8 brain respond to?
So we don't have the algebra for the solid partition, so we don't have any answer for that.
So for that, you lose its ability to avoid
It shouldn't be content void algebra, but it should be a different, higher version of it.
because you see explicit Q3 up here.
Yes. But for the moment, we don't have all of the answers. And also a different aspect of it is that so for the D6 partition function, you can take the undefined limit and you have a character. So that means you're expecting you have some kind of algebra. But for the D8 case, naively you cannot take that limit because you have Q1, Q2, Q3, Q4, everything is symmetric, but if you naively take to one limit, everything diverges. So you may not have an algebra, but I don't. But recently, there's also already an algebra associated to all of this, a new type of quiver algebras for acting on solid partitions. So maybe there should be some relation with that, but I don't know.
So in the quiver for C4 at the beginning,
Yes.
you have both chirals and Fermi. Do the Fermi multiplets contribute to the superpotential?
Yes. At the yes. Which one? This one here?
Right. Yeah.
Yes. Generally, all this Fermi multiplets also contributes to the super J terms and E terms.
So all these relations, do you have a superpotential for them, or you just have the relations?
So for C4, everything is known. Also for the quivers associated to the brain tilings and brain brick models, you have all of these J terms and E terms when you don't have, I think, the framing nodes. So the concept for gauge origami is the concept of classifying the possible framing nodes. So for brain tilings and brain brick models, you need to classify first these framing nodes and then study the J terms and E terms and derive the fibers and do everything. Yes.
And the Lagrangian contains Fermi J and Fermi E couplings.
Oh,
Any other questions? Yeah, Masahito?
Yeah, so the question is that, so it's a bit of a general question about this KQ character. So in this story, you start with a partition function.
Yes.
Right? So the multiplication expectation by sum of it.
Yes.
Then you get rid of the multiplication expectation by part and then extract the
Yes.
out. So that's the story.
Yes.
And then the question is that is there and it seems to work in many examples, but is there a conceptual understanding why that algebra acts on BPS states? To some extent, you are writing that expression and massaging it, and there's algebra, and then strictly speaking, there is not a unique way to extract algebra that way.
Yes.
Presumably, there are many, many different ways of writing the same expressions. And
Yes, yes,
so not the canonical algebra, so to speak.
yes.
In
So
practice, of course, you have some specific expressions,
Yeah.
so not natural algebra. But then the question is that if you follow that procedure somewhat more generally, then is there a guarantee that that algebra actually acts on BPS states?
So for the moment, we don't know. So that's the reason why we're just trying for the moment extending everything. But I think that's related to question the physical physical meaning of all of these QQ characters. But I think that's still an open problem. So we need a more nice physical discussion why all of these QQ characters appear. But for the moment, all of them before our work, it was like only focusing on finite fiber types. So for the moment, we're just extending it. So my answer is I don't know, but that is a problem that we need to understand.
Yeah. So and for the D4 cases, there's a realization of the QQ characters from the R matrices of the relation.
Yes.
That
So
we partially answered.
one expectation of it is the D6 will be R match of the Mach-Moh module, and I think that will be also the answer. But
Still questionable for D8.
D8 still.
Not good.
For the D6 case, we know since you have a QQ character, right? We know what kind of intervals that may associate.
No, so that's the question I want to ask you. So for also D6 case and also the QQ characters associated with brain tilings, you all have this expression. So the question is what kind of integral system it is related to.
Any more questions? If not, let's thank Corey again.